the timer started, so I better get going. So today I'm here to talk about OpenJ9 and the different GC technologies that are available in the OpenJ9 JVM. So quickly, some important disclaimers. I work for IBM, so I have to put these up here. Just basically is saying that don't base any business decisions on what I say today. So about me, my name is Charlie Gracie. I'm a senior software developer at IBM. I work in the runtimes team as the garbage collection architect. I'm also the project lead on 2 Eclipse projects, the Eclipse OMR project, and of course, and I'm a committer on the Eclipse OpenJ9 project. And I've been working on garbage collection technology for about, I always say 10 plus years, but it's closer to 15 now. And with most of the time on the team, I've been focused on high scalability and throughput for the GC. So today, I'm going to give everyone just a really quick intro into the OpenJ9 project and Java Virtual Machine. Just a bit of details on it, in case you're not aware of what it is. Then I'm going to just another quick overview of garbage collection in general. And then I'm going to jump into a deep dive on some of the GC technologies in OpenJ9, and then end up with some conclusions and open the floor for any questions if we have time. So, OpenJ9. OpenJ9 is actually a completely compliant Java virtual machine was open sourced last September in 2017. It's actually not a new JVM. It's actually been the IBM's Java virtual machine for about 17 years. It's got a full compiler and GC and very scalable GC technology. It was open sourced under EPL v2 and Apache license. You can go to GitHub, check it out. It's basically a drop-in replacement for Hotspot in an OpenJDK package. And we're always looking for contributors or questions, issues. Feel free to jump on GitHub and check it out. You can go and start from GitHub and you can download and build the OpenJDK with OpenJ9 yourself. But I know a lot of people don't build their VM themselves. I don't blame you. So if you want an easy place to go get OpenJDK VMs with Hotspot or OpenJ9, there's Adopt OpenJDK. It's run by the London Jug, and they're actually grabbing different versions of OpenJDK, building them and providing the binaries for everybody. They also build nightly Docker images based off of Ubuntu 16.04 that they actually just go and package the different JVMs in, so you can get that as well. So one other quick thing is the Eclipse OMR project. This is actually a little bit older. It was released it's almost 2 years old. So what it is we actually took the GC, JIT, and a few other technologies from our VM, and we actually realized that those weren't Java specific for the most part. You could reuse the GC or the compiler technology in other runtimes. So the first step to open sourcing the VM was to actually go and open source our toolkit for building runtimes. This is consumed back into OpenJ9 daily and is the basis for all of the technology that's there. All right, garbage collection. The reason we're here for the talk today. So garbage collection is basically a form of automatic memory management, and this is there to actually help the user remove some of the constraints on the user for monitoring the memory usage themselves. Basically, the garbage collector will help you allocate objects and it will reclaim the memory for those once you're not using them anymore. So the responsibilities of the GC are those 2 things, basically pretty simple. It allocates objects, and it'll reclaim the objects once they're no longer required. The one main point here that I want to emphasize is it'll ensure objects remain at least as long as they're required. There's actually no description or requirement on when the garbage collector will actually collect an object, so it could actually live way longer than you think it should. the GC is free to collect it at any point in the future after it's not referenced. And another part of the GC is to also ensure that object finalizers and reference objects are processed before the object is collected. So some of the positives about garbage collection is just the automatic memory management itself. And what comes along with this automatic memory management is it actually helps reduce a certain different types of bugs that you can have in your code. Dangling pointers, double freeze, and these types of things aren't usually a problem, unless of course the GC is actually the problem in this case, but we hope that that's not the case. But the negatives are what I hear about all the time, and so that's kind of want to talk about the GC technology today. But a lot of the negatives are, you start up your JVM with, say, a 2 gigabyte heap, but you look at your process and it's using 3, 4 gigs. So everybody wants to know why. So there are a lot of actual other required resources depending on the GC technologies that you're using. Of course, the GC can cause unpredictable pause times, and I assume everybody here who's running Java actually has come across the GC getting in their way. There's also some other hidden runtime costs that you might not be aware of. So depending on the type of GC technology you're using, you may have to introduce, the VM may be introducing read or write barriers into all of your object accesses. So these can actually be quite costly as well, especially if you have to have a read barrier because you're constantly fetching fields out of objects. So it can actually be a very heavyweight operation. And also your application has very little control over when the memory is reclaimed. So let's jump into the GC's technology in OpenJ9. So there's a whole host of GC policies here. For the talk today, I'm not going to talk about the first two at all. They're sort of deprecated old. They were some of the original GC policies that we had. I haven't recommended anybody use them in probably 5 years or more, so I didn't figure there was any reason to go through and talk about them today. But the good part is all of the different policies inside our JVM all rely on the same technology as a base. So as I cover the GencOn GC policy, it actually completely encompasses all of the technology in the top 2 collectors that I'm not talking about today. So the GencOn collector is actually our generational copying collector that has a global, concurrent global collector to clean up the old space. There is a sub option for this GC policy that was just introduced last year. But again, I won't talk about it today because it's actually only available on Z14 hardware. And I didn't figure that there was that many people here that actually had a mainframe sitting in their basements, so I figured I would skip that one for today. Metronome, which I hope is interesting to people, is a soft real-time incremental GC. This one has some very low pause time characteristics, and it's actually been available on our VM for about, I would say, 7 or 8 years. So it's very mature, and it actually provides very low pause times. And then I'd also like to talk about balanced GeeCOPolicy, which is a region-based collector quite similar in practice to G1 in Hotspot. So the GencOn GeeCOPolicy is actually 2 different collectors under the covers. There's actually the copying collector for the nursery collections, and this is basically taking advantage of the weak generational hypothesis that says that most objects actually die very young in age, and also that objects of similar age tend to die at the same time. So you'll actually focus your collection on a small area of the heap that you do all of your allocations in to actually have smaller pauses. And then at some point your heap will actually fill up, so you need a global collector to clean up the whole heap. So we have a concurrent mark sweep collector to do the rest of that. The one interesting fact about our concurrent GC that I'm not sure any of the other GCs out there have is we actually do a lot of the concurrent work on the application threads themselves. So they'll actually pay a tax when they allocate and perform little tiny bits of GC work themselves to actually help push the GC along and not have any long global pauses. So GencON has a lot of native memory extra that you might not realize. There's actually native memory for mark maps, because that's how we do things in the global GC, and work packets. There's a card table for remembering information. I'll cover more of these as the slides go on, but I'm just kind of mentioning them now so everyone can notice when they come up later. And copy scan caches for doing the copying. Because it has these two different collectors, it also introduces and has to have two write barriers. So as every object store you do in your VM, there's actually going to be two different barrier checks and work done for those. This basically is our default collector, and for most applications will provide you the best throughput for the average best pause times. So how does GencON work? So the heap, I'll go through first and talk about sort of the heap layout, and then talk about how the GC works, and then dig into some of the details. So the heap is divided into the nursery and tenure area. The nursery is usually smaller. You can configure it so it's larger, but by default it's 25% of the heap. But then the nursery is also subdivided into two spaces itself, allocate and survivor. As the name suggests, all of your objects are allocated in allocate space. With an asterisk there, some objects that we expect to live a really long time, like classes and intern strings, they go directly into tenured space. So what does it actually look like when you have this memory and you're allocating? So both the allocate space and tenure space would have a free list for allocations to happen. And you would allocate along. And at the time allocate space is full, you'll actually need to now stop and do a GC. And you'll see that during startup and things, there are a lot of allocations in tenure space, so I kind of showed that there would be some there. So what happens for the GC is everything in allocate space, the GC will then go and copy the live objects into survivor space. And anything that needs to be tenured into tenure. What happens then is we actually just change the names. Allocate space becomes survivor space, and survivor becomes allocate. So at this point, then the free list now has more memory. We have more memory to go back and use again. So then the GC gives up the GC time and lets the application start up again. So let's just pretend this kept going for a while. You kept tenuring more objects and more objects every GC that happened. Eventually, at some point, you're going to want to do a global collection. So at this point, we would kick off a global GC. But like I said earlier, this GC actually does a lot of the work concurrently. So you kick off, and then you would actually see that more allocations happen and more GCs happen until the point where we've realized it's done enough work that we would actually go and stop and complete the GC. So at this point, we would go through and we would have finished off all of enough work we believe to complete the GC, and we would stop and do the final collection of the GC. At this point, it actually collects the whole heap. So you would see that objects, and there's more free memory and allocate space, and that there's also free memory and tenure space now after it's done. It doesn't do any compacting or moving by default most of the time, so you will have sort of this fragmented view of the live objects. So that's sort of what the heap looks like during GC. So now I kind of want to show what would your application look like, or how much would your application be running when you're using this type of Xecpolicy. So the blue lines are application threads executing. Whenever we would have to stop to do one of the nursery or scavenge collects, none of your application runs anymore. So we pause for a short time, you do a GC, again go back, another GC. This one shows that we would kick off a global GC, but the interesting part follows this, is when we start back up, there's a background thread that will actually be processing things concurrently, And you can see in the application threads, the yellow spots are when the thread for the application actually stopped to do some GC work as well. And while you're actually in a concurrent GC, you could also still stop and do a scavenge. It doesn't interrupt it. It just keeps going as if nothing happened. You would go back, continue doing your global GC work and your application running. You stop again to pause for the finish of the global, and once it's done, your application will go back. So this I just wanted to sort of illustrate the fact that they could be happening at this interleaved, and that the scavenges didn't have any real impact on the concurrence. So, what is the generational copying collector? How does it work? So before I get into exactly how it works, I want to talk about the generational write barrier, what it is, why it's needed, and what cost it has to your application. So why it's needed is the GC actually needs to be able to find objects in the nursery that are referenced only from the tenure space. If we didn't keep track of those objects, we wouldn't know about the object references in nursery that are only kept alive from there, and you'd end up with dangling pointers after a GC. So what this basically means is that if you had this simple set field method, it would look just like this: A field 1 equals C. But in reality, when the VM actually runs that code, it's actually inserted all of this code after the store to be able to track things for the GC. So basically it goes, if A is a tenure space and C is not in tenure space, then we need to remember A for future processing as part of the GC. All right, so how does the GC actually work now that we've covered the barrier? So this is sort of a zoomed in portion of the heap. Hopefully you'd always have more than about 10 objects. So what happens when we stop to do a GC, the first thing we need to actually do is define some root set, or the primordial list of objects that are alive that keep everything else alive. So this is a well-known thing for the VM, so the first thing the GC does is it will actually start walking the root set to find objects that are alive. Once it finds an object that's alive, it needs to do something with it. So in the generational collector, it's actually going to copy the object, as I showed before, from the allocate space into survivor. So every thread that's running as part of the GC would actually end up with this scan and copy cache mechanism. So as you find objects alive, you copy them into your copy cache. As copy caches become full, they get put on a list and become scan caches, and then you just keep going recursively until all of them are empty. So what you would do is you would copy A from its old location to its new location and install a forwarding pointer. The interesting thing about the forwarding pointer is this is how if you find this object again from somewhere else, that you know it was already actually processed by the GC. So in the header of the object that was there, we actually store a forwarding pointer to the new location and copy it into the copy cache and update the reference from it. So the root set now also points the reference to A prime as well. So we'll do the same thing for D. It gets copied, F. Now we're actually finished our root set. So the copy cache that we have, actually, there's no more work for us. So we'd have to we would flush this cache. So everyone's output copy caches go over to this work list. And then you would actually go grab one. In this case, it's just grabbing back the cache it had itself. But it also needs a copy cache. Luckily, this scan cache also still has space in it, so it gets aliased over as your copy cache as well. So what we do at this point is you would start scanning your scan cache to find other references that are alive. So from A1, it actually pointed back at C, so we'd copy C over. There's nothing else that A points to, so we'd move on to D. D has a stale pointer to F. That gets updated to F prime. F has a similar thing. Actually, F had nothing, so there's nothing to do. C1 points to a stale pointer as well, so it just gets updated. And then we're finished. We're finished our scan cache, so we would push this as it's done, and we'd go try and get another one, and we'd just keep recursing over that till we're finished. And at the point where we're finished, then we actually have our work list and all these things empty, and that's the end of your scavenge. The survivor space becomes allocate, allocate is survivor, and we move on to the application running again. So the next part of GenCon would actually be the marked sweep collector. So this actually, eventually tenure space gets filled up and you need to collect it. So you would do this concurrent mark and sweep GC. This GC is divided into 3 stages. There's marking and sweeping, which are run every GC. And then there's an optional compactor that runs only if your heap gets really fragmented. The compactor is quite slow compared to the rest of the operations. We can't run it in concurrently with your application, so we try our best to never run this. And this is where you would start to see the multi-second pauses in a GC that nobody wants to see. So that's why it's not run very often. So global marking. Again, if we zoom in on a portion of the heap, we can actually go and see that we have these objects. So how will we do a GC? So again, we'd start with our root set. And from the root set, we also, another data structure that we have in the GC is the mark map. So this mark map, actually, there is 1 bit in the mark map represents 8 bytes on the heap. And due to our object alignment of minimum 8 bytes, we can always map an object to a bit in the mark map. And we also need a data structure to track these references. So similar to the caches that we had of copy and scan, we have some input and output packets. So first thing we do, again, we're going to start scanning the root set. And once we're scanning the root set, we'll take the first object. We'll mark its mark bit. We'll find the right location in the mark map, set the bit, and push the object on an output packet. The input and output packets are done as a stack. So we continue to go through. We mark all of the objects that were in the root set. We're done processing the root set now. Similarly as the copy cache, we would end up flushing all of our full caches over to this work list, and then we would have to go and pull one of the lists off again to handle for ourselves to do some work. So once we have one in our input packet, we would pop off the first let's add some references so we have something to trace. So we pop L off of this work stack. We see that it points at object M. Object M in the mark map, its bit isn't set, so we set the bit and push M on an output packet. Similarly, we do for I, it points to K. D points to F. A's first reference points to C. Since C is already marked in the mark map, we don't do anything. We never actually process an object twice, not just because you don't want to end up paying all this cost, so you're always checking the mark map before you do any work. So an object will never get onto the work stack via regular marking more than once. So then A also points to B. It goes on. Again, we'd flush the packet. And once this is all done, we would actually be complete. Once there's no more packets on the work list anymore, we would be finished that part of the GC. But I said that this GC is actually happening concurrently. So if this is happening concurrently, you would do some marking. You would mark objects, scan a few objects, and then you go back and let the application run. So once you've done that, we actually need to introduce another write barrier that I mentioned before. We have a concurrent write barrier. The reason that this one's required is this. If this is basically the same map I was showing before, we have all of these objects and their references marked. If we actually switched the pointer that I was pointing at K to point at C after we've done marking, I said earlier, we would never put an object onto the work stack again, so there's no way we would ever scan I again. That means that we're going to end up with a dangling pointer to C. Since nobody else references it, at the end of the GC, we're going to collect it, and it's gone. So what we actually do here, oh, that's just showing that it was marked. So what we do is, again, we have another write barrier. So again, if you look at this simple set field, what this would look like for the concurrent GC is after we've actually written it, the VM's going to go insert a check to see if the concurrent GC is active. And if it is, we're going to dirty a card in our card table, which I'll talk about shortly, for this object. Now, we're in GencOn. I already talked about a barrier that's there. So in fact, this is actually what every object store looks like in your VM when you're running a collector like this. You would actually set the field, and then you have all of these checks and extra work that's going to happen for every store. Luckily, we have just-in-time compilers and things that are going to actually coalesce a bunch of these barriers or actually remove them completely if they know it doesn't have to be there. But when you're running in the interpreter, every time you store, this will happen. So how does the write barrier actually work for this one? We have this card table structure. So the card table is actually 512 bytes of the heap is represented by 1 byte in the card table. So what we would do at this point is when we change the reference, we're actually going to go find the appropriate byte in the card table for this area that we are in the heap, and we're going to set that that card is now dirty so that we have to process it later as part of the GC. So if we went back now, before I said we were done our global marking, what we actually have is one other phase. We actually have to go do card cleaning before we can actually finish the GC. So what we do at this point is we actually will walk the card table, we look for dirty cards, and then we'll go through and we will find one, and then we go to the mark map for that area. Every object that's marked in the mark map, we have to go rescan again. So in this case, we would find I, it's marked, we would go rescan it. It points to C. C is not marked. We mark it, put it on an output packet, move on. We find the next one in there marked. There's nothing to do in that area, and then we're finished. So again, we would actually just be complete at this part, and then we would process these input and output packets the same as we did for the rest of it. Once we're finished that, we now are actually finished marking. So sweeping. When we look at sweeping, what happens is you're actually going to take this mark map that we built during marking, and you're actually going to walk it looking for zeros. This happens in parallel, so the mark map will get divided into different sections for different threads, and it will walk looking for zeros. Every time it finds a 0, it would go create a free list entry. This is a very simple example. To be performant, the GC actually wouldn't create free list entries for every single object. There's actually a minimum size of 512 bytes. So that means you would actually have to have 64 zeros in a row before we'd actually go create any sort of free list entry. So let's assume these boxes, the small boxes, are 256 bytes of size. So in fact, we would actually only end up with 2 free list entries after this GC. A lot of the time, that's probably enough memory. But in cases when this really starts to get small and you don't have enough, what we actually need to do, and a worst case, which we try to avoid, is we might actually have to go and do a compaction. So for the compaction, we need another table so that we can do work. But I didn't list the compact table as something that was an extra thing for this GC. It's because it's not. We actually compress our mark map, and we use the other half of the mark map as the compact table. So what we do, what would happen in compaction, is you would actually go through, move every object, but by how much it slides. Everything slides from right to left. However many bytes it slides, that actually gets stored in the compact table as an offset. So the first object moved 256, the next one's 512. I picked these numbers because they're easy math. 1024, and so on and so forth, until all of your objects are moved down. So at this point, we just have one really large free list entry, and we're done. But not quite. We've only moved the objects. That's actually, in general case, the faster part of the operation. The really slow part of the operation is now that we've moved some portion of the objects, we actually don't know which objects pointed at what objects, so we actually have to walk the entire heap to actually go fix up every pointer and every object reference that was in the heap. So a quick example would be if A pointed at D, we'll have to go through, because it's just sliding to the left, we just know that it's the old address of D minus the entry in the compact table, which is 256, and then we would just store that back. But we actually have to do this for every single reference in the heap. This can be very time consuming and basically destroys all of your caches. So that's sort of the end of how GencON works. The next collector that I want to talk about is the metronome GC. The metronome GC is developed as an incremental real-time collector. For a few releases, the IBM JVM actually supported a fully compliant RTSJ1 version of the spec, which was a hard real-time VM and GC as long as you ran on one particular type of hardware, on one particular OS, it was fully supported. As we were developing that, the only way we could come up with to do the GC was this incremental collector. So what it basically does is it only has a mark and sweep. There's no compaction ever because it's just too costly. It, by default, has pause times goals of 3 milliseconds. And it has a guarantee for the application that it will let the application run 70% of any timing window. Both of those options are configurable, and I've seen people in production running with 1 millisecond pause goals and 90% application utilization. The utilization really only is a concern during GCs, but if you're actually regularly quite full on your heap, it really starts to show up. So regularly, metronome will actually only be 70% of the throughput of some of the other collectors. But you get this really cool 3 millisecond pause time at any one time. It uses a snapshot at the beginning barrier, which I'll talk about later, and it has probably the lowest extra footprint of all the collectors that I talk about today for off-heap memory, of only having a single mark map, work packets, and a remembered set. So in metronome, the heap is actually divided into regions. All regions are 64K in size, so the bigger your heap, the more regions you have. The region size is small so that we can process things and be able to handle them and meet our pause time guarantees. It has a cell-based allocator, so every region is assigned a cell size the first time it's used. So if you're allocating an object of size that requires 16 bytes, when you allocate it in this region for the first time, now every object in that region will only ever be 16 bytes. If you have a different size, you need a different region. The cell sizes go from 16 bytes up to 2K. So objects larger than 2K actually need to consume multiple regions, but they actually have to be contiguous. So if we don't have enough contiguous regions for those objects, out of memory. That's not super common, but it has been a thing that we had to look at. Because most large objects are actually arrays. So what we do for arrays is we actually allocate them as arraylets. So what's an arraylet? An arraylet is a discontiguous representation of arrays. It's allocated with a spine and one or more arraylet leaves. And in metronome, arraylet leaves are 2K in size. So what this looks like is you actually have your arraylet spine, which contains pointers to the leaves, and if there's any extra data, it's another pointer down into where that data is embedded in the object itself. So even a really small array of one entry has one wasted slot to point down to where the data section is. There's always at least one leaf pointer, even if it's just to the internal data in the object. There's the calculations how you figure out which leaf, and then how you index into the leaf. So with that extra cost is array access can be quite a bit slower because there's some calculation and at least one extra dereference, but allows us to represent really large arrays and still be able to meet our pause time goals because we only have to handle up to 2K of data at any one time. The one really big drawback is if you're doing JNI and you do JNI critical sections on primitive arrays, we need to hand back a contiguous view of the object data so that you can handle it. What that means is we copy all of the memory from your object into one contiguous native buffer, give it to you, you process it, you give it back, and we copy all of the data in again. So it actually can be quite slow there. So what does it look like for allocation in metronome? You're going to just slowly see different regions fill up because you actually have different cell sizes. Once we get to 50% full, we'll kick off a GC. You'll still see that while the GC is happening, more objects allocated because we're just doing a small amount of GC work, letting the application go again. And then basically by the time marking is done, we're pretty much completely full on the heap. We usually like to leave a little slack, but it's usually pretty full. And then the sweep phase will start, so we'll keep doing increments again of sweep work. And you'll see over time, the heap is slowly getting freer, even though you're continuing to allocate. Once the GC cycle is complete, the last sweep increments happened. If you're unlucky and you're actually 50% or less free again, another GC is kicked off immediately. So if you are running right on the kind of boundary of your heap, you will be in this continuous GC mode. And at that point, if you're actually just using the default 70% utilization, your application will be about 70% of the speed of the other collectors. So how does this look? If we just sort of look at the charts, the flow graph here, application, then you would actually stop and start the GC increment. You would now have these application increments that are basically the same length as a GC increment. It's going to be 3 milliseconds GC, 3 milliseconds application. After the fourth one, you would actually now be down so that you didn't meet your 70% goal. So we'd actually do 2 application increments in a row so that we keep back up to above 70%. So this would go until you finish. The metronome snapshot at the beginning barrier is slightly different than the other barriers that I showed before. This barrier actually states that from the time we start the GC, every object that was alive at that point until we get to the very end of the GC is alive. So this can actually quite a bit of floating garbage. And this barrier has to be performed before the store. So what it looks like, as we've seen the example a few times now, you actually fetch the field into basically a temp. If your barrier is active, you actually remember the object you're overwriting, because this barrier says everything that was alive will stay alive. So everything will have, you remember that one, and then you actually store the field. So the metronome GC, again, sort of starts when it's 50% full. These GCs will be triggered or started by an alarm thread that runs, wakes up every 1 millisecond, checks to see if a GC should happen, or during out-of-line allocation, in case that thread doesn't get the chance to run, an application thread will also do a similar check and go, oh, it's time for the GC, we better wake it up again. One key point about this GC compared to the other ones is usually our GC outputs verbose GC data per GC cycle. Well, we don't want to be able to do every GC pause output because that's every few milliseconds. So it actually summarizes the data across X number of increments and outputs it every 1 second to your verbose log if you were gathering verbose data. The marking and sweeping uses exactly the same data structures and algorithms as the global collector I talked about before. Kind of a key goal of ours is to reuse as much of the technology in any one collector as we can in the others. The only slight difference is during root scanning, marking, and sweeping, we insert a bunch of should yield checks. And anytime we should yield, we actually pause and go back and let the application run. So no demo really here of the GC tech because it's exactly the same, but what I'm showing here is in the normal collectors, the other one that we were showing before with marking, this is basically the work loop. While there's objects on your work stack, you scan them until you get nothing back, and then everyone's done, and the GC is over. The subtle difference in the metronome collector is you get work, you kind of keep track of how many pointers you scanned. When you've crossed some magic threshold, it's kind of different depending on which phase of the GC you're in. You check if you should yield. That cond yield checks and yields if you need to. And if you did, when you come back, you just start over and keep checking again. So that's it for the metronome GC. Balanced. It's a region-based collector. Its goal was to actually sort of balance out your pause times and your throughput. So with GencOn, we have really great throughput that I talked about before, but you can have these outliers of compactions and things that will take seconds. So if that's actually going to be detrimental to your app, you may not be able to run it. The other option is the metronome answer, where we guarantee really small pauses, but you take a pretty hefty throughput loss. So the idea with balanced is that we would actually try and remove the global collections completely by including parts of the old objects in every one of the nursery collections. So we don't call them nursery collections, we call them partial garbage collections, because they're always going to collect some portion of the heap. Then there's the GMP phase. This actually just rebuilds mark maps and things for the GC so that it has an accurate picture of the whole heap when it needs to do any work. One difference from some of the other collectors like G1 is this one is fully NUMA aware for allocation and during GC. So if you're on a large NUMA system, this can actually provide pretty significant throughput. So again, the balanced heap looks kind of like the metronome one. It's divided into regions, but all of these regions are slightly different than in metronome. Region size here is a power of 2. The size is a power of 2. We try and have between 1 and 2,000 regions. So the bigger your heap, the bigger the region size. Where in metronome, the bigger your heap was more regions. And these regions are evenly distributed across the NUMA nodes for allocation and GC purposes. So a difference from metronome, non-array objects cannot be larger than a single region. If it's actually larger than a single region that you try and allocate an object, immediately and out of memory. Or we return null and that the VM's going to return it out of memory. Region size usually tends to be in the small number of megabytes or larger, so this usually isn't a problem. Again, large arrays are turned into arraylets. The arraylet size here is slightly different. The leaves are actually completely full regions. So how does allocation work? In this one, allocation happens in Eden regions. In the GencOn, it was in contiguous section called allocate space. Here, any free region can actually become part of Eden space. So we don't have the restriction of it having to be in one spot. We can grab any free region. And we actually try and grab regions from different NUMA nodes so that we can distribute the work. And in most of the time, we bind application threads to a particular node, so they're always working on the same node as the memory they're using for the most part. So if this was our Eden set, the light blue ones, what would allocation look like? You would sort of slowly go through, fill it up, and at that point, it's time for a PGC. So let's make it a little bit more complicated. Let's assume it's not the first GC of the run. So the green ones were the fully allocated Eden space. And, okay, it's still orange up there. The orange ones are older objects that have been survived for other GCs. So we have to select the regions we want to include for this PGC. Immediately, we're always going to include all of the Eden regions for the same reason that we always collect the allocate space in the nursery, These are the most recently allocated, so there's likely the highest return on investment here because a large portion of these objects probably die very quickly. And then we'll select some of the older regions based on some statistics that we've gathered based from the GMP that I talked about, gathering data to see which ones might have a good return on investment. So we would collect those, and you can see the objects that are alive move somewhere else, and relocalizes them all and copies them onto their same NUMA node. That would be performing the copy forward collection. Once it's done, we'd assume all of those objects are old, and then we would pick new Eden regions and keep going again. So what does this sort of look like? If your application was running, you would do PGCs, and we actually try and do the GMPs in between PGCs. So we kind of guesstimate on how long it takes in between PGCs, and we'll try and schedule a GMP increment in between all of those so that our pause times are kind of easily distributed and always of a similar size. The PGC will only do as much work in a stop the world as the average PGC pause. Whenever it reaches that, it just sort of aborts and goes on back to the application and will resume afterwards again, just to sort of keep this even keel of pauses all the time. So we go through some more PGCs, and then GMP ends in another PGC. So the real important part of this is that GMP phases actually never reclaim memory. They don't do any real collection work. All they do is actually track live object references and build a new mark map that the PGC can use for collection afterwards. So balanced also has a write barrier. This is required because PGCs, similar to a nursery collect, need to know references that point into the objects that are being collected. So we have to track this. And the one for balanced is actually very simple. It's the simplest barrier we have. You just dirty the card for every object all the time. So the PGC, it performs its copy forward operations exactly like GencON. It has the same copy and scan caches, processes the data the exact same way, with one small caveat. It also sets mark bits the same as the global collector that I was talking about as well. It uses the forwarding pointer the whole time to track whether or not objects have moved, but it keeps this mark map up to date as well just for future reference to know which objects are alive anywhere, to be able to know which regions to include in the collection set. If at any point there isn't enough memory to copy into, because we have this mark map, we can actually complete this PGC as a mark sweep compact PGC. Don't like to do that, but if we actually run out of memory to copy into, we could fall back to that. And one interesting side effect is we can actually do class unloading in the PGCs. So sort of my conclusion is I have a quick sort of guide here of the different GCs. GencON is our default collector. For most web applications, even your desktop applications, it's probably the collector that is going to give you the best bang for your buck. That's why it's our default still, and we actually aren't really considering making balanced our default similarly to how G1 is the default, just because of the overhead of throughput and things that happen in those collectors. And the sort of memory there is that's percent of XMX of how much off-heap memory these collectors actually consume, extra compared to your heap. So balanced, I'd recommend this if you're doing very large heaps, something over 20 gigabytes, 50 gigabytes, terabytes. That's where balanced really starts to show you some wins. And again, especially if you're on really large NUMA systems, you'll actually see some pretty nice throughput wins, especially if you're on like a 4-way NUMA machine. Metronome, if you want really low pause times because you can't handle any real interruptions for the GC and you can tolerate some performance loss, this is where you need to be. So sort of the takeaways from today, I hope everyone, if you didn't know about OpenJ9, now knows about it as an alternative for JVMs that can run with the OpenJDK JDK. I hope you have a bit better understanding about how some different GC technologies work. The tech here all is quite similar to what's in Hotspot and other VMs, and I sort of hope you're willing to go try some different GCs as part of your application because it may make some differences to your throughput or pause times. Some quick links if you want to go check out the projects and questions, but I just got to zeros, so I don't think we have time right now.
Got it. I was wondering, the last two GCs, how do we deal with large strings, which is something that happens very frequently in applications, especially big JSON stuff, XML, so copied in memory. How do you deal with those?
So a string is actually an object that has a pointer to a char array for the data. So the string object would be exactly the same as it would be in any other GeeCOPolicy. And then the char array, if it needed to be, would be turned into an arraylet and spread across the different memory locations.
Okay, thank you.
You're welcome. Okay, well, I thank everybody for showing up this morning for a 9 a.m. talk.